Welcome to the first module of the Vetecs Automotive Installer Course, the Introduction to Automotive Electrical Systems. This course is meant for individuals interested in a career as an automotive installer or existing technicians wanting to improve their skills and knowledge. The full Automotive Installer Course consists of 3 modules. Module 1, Basic Automotive Electrical Theory. Module 2, Installation Techniques. Module 3, Advanced Techniques and Circuits. This is Module 1, Basic Automotive Electrical Theory, and will cover the following topics. Basic Electrical Theory. Basic Wiring Diagram and Components. Basic Automotive Electrical Power Circuit. Basic use of a multimeter. It is important to understand the fundamentals of electricity and automotive electrical circuits. Having a basic understanding of these concepts will greatly improve the quality of your installations and your ability to troubleshoot problems. The first concept we would like to discuss is electricity itself. Electricity is defined as the movement of electrons, which creates charge. This might sound complicated at first, and it has probably been a while since you were taught these concepts in school. What makes it more confusing is the fact that electricity is invisible. The easiest way to explain electricity is to compare it to the flow of water. Imagine you had 2 containers connected to each other by means of a pipe and a valve. If the first container is filled with water and the valve is closed, no water will flow to the second container. The first container resembles a battery, and the potential of the water that can flow from one container to the other resembles the potential difference. Voltage is defined as the difference in charge between 2 points, called the potential energy difference, and is measured in volts. Voltage is displayed using the symbol V. The valve represents an on-off switch. When the valve is opened, water will flow from the first container to the second, just like electrons start moving when a switch is turned on. In the previous example, the valve was opened fully to let the water flow from one container to another. If the valve is opened slightly, water will still flow, but very slowly. This is due to the increased resistance caused by the smaller opening. The same applies to electricity. Any resistance in an electrical circuit will slow down the flow of electrons. Resistance is measured in ohm and is displayed using the symbol ohm. In the previous examples, we discussed the movement of electrons. The rate at which electrons or charge flows is referred to as the current flow. Current is measured in ampere, or amps, and is displayed using the symbol A. There are 2 main types of current flow, namely direct current, referred to as DC, and alternating current, referred to as AC. Direct current is current flowing in one direction and has polarity of positive and negative. Alternating current is current that continuously changes direction in flow. The automotive electrical system is mainly DC, and utilizes a 12-volt or 24-volt battery to power the circuit. The battery is charged by the alternator that generates AC, which is converted to DC. Let's summarize what we have learned. Voltage is defined as the difference in charge between 2 points, called the potential energy difference, and is measured in volts. Voltage is displayed using the symbol V. Resistance is the tendency to resist the flow of current. Resistance is measured in ohm and is displayed using the symbol ohm, or R. The rate at which electrons, or charge, is flowing is referred to as the current flow. Current is measured in ampere, or amps, and is displayed using the symbol A, or I. There are 2 main types of current flow, namely direct current, referred to as DC, and alternating current, referred to as AC. This section explains how these values can be calculated. The values for each of these parameters, volt, V, ampere, I, and ohm R, can be calculated by applying Ohm's law, which states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. The formula for this calculation is V equals I times R, meaning the potential difference, or volt, is equal to the current in ampere multiplied by the resistance. The current can therefore be calculated by dividing the potential difference by the resistance. Therefore, we can conclude that the current in an electrical circuit measured in ampere is dependent on the amount of resistance in an electrical circuit measured in ohm, and the potential difference in an electrical circuit measured in volt. Here are some examples. Let's say we have a 12-volt power source with a 100 ohm resistor. We can now calculate the amount of current flow as follows. I equals V divided by R. Therefore, I equals 12 divided by 100. I is therefore 0.12 amps. In the next example, we have a 12-volt power source, and we measure a current flow of 3 amps with a multimeter. We can now calculate the amount of resistance as follows. R equals V divided by I. Therefore, R equals 12 divided by 3. R is therefore 4 ohms. Another concept associated with Ohm's law is electrical power, represented by the symbol P. Electrical power is the rate at which energy is absorbed or produced within a circuit, measured in watt, represented by the symbol W. Let's compare the previous example of water flow to an electrical circuit. The components in an electrical circuit are represented by individual circuit diagram symbols. The first component we will add is the battery symbol housing the potential energy which represents to the reservoir with water. The second component we will add is the switch representing the valve. The third component we will add is the resistor representing the size of the valve opening. Let's add another resistor in the form of a light bulb. The fourth component we will add is the conductor connecting the components which represents the pipe. We would now like to raise an important point. Conductors and components can only tolerate a certain amount of current, and therefore a minimum resistance is required in an electrical circuit to ensure the maximum current flow is not exceeded. If the resistance is too low or is non-existent, the rapid current flow could generate an immense amount of heat and could melt conductors and cause damage to components. This is referred to a short circuit. Therefore, the final component we will add is a fuse that prevents excessive current flow and resembles a pressure valve that can be used in a water flow system. Let's use the components from the previous section to build a basic automotive power circuit. In this diagram, the battery represents the 12-volt vehicle battery. The light bulb in the circuit represents a light that turns on when the ignition is switched on. The negative connection, or ground connection as it is known, is represented with the ground symbol used in automotive circuits. Automotive circuit diagrams seldom show ground wires, as the battery ground is usually connected to the vehicle, the body, or chassis, and therefore ground connections to components can be achieved by connecting them to the body or chassis. Next, we will replace the switch in the diagram with the ignition switch. This is a two-pole switch with the first position providing power to the ignition circuit and the second position providing momentary power to the starter circuit, only while it is held in that position. We will now look at a practical example of our diagram. The power connector resembles our 12-volt power source or battery. The negative side of our battery is connected to our common ground, which is a metal plate. The positive side is connected to our switch. The other side of our switch is connected to our fuse. In this case, we are using a 7.5 amp fuse. The negative side of the light bulb is connected to our common ground. Current is currently not flowing through the circuit as the switch is off. When we turn the switch on, we complete the circuit, and current can flow through turning the light bulb on. We will now build on the previous circuit and will add the starter circuit that enables the engine to be cranked by turning the ignition key to the momentary start position. The starter motor consists of a 12-volt solenoid and a high-current DC motor. The solenoid is a dual-purpose electromagnet. When power is applied to it, the current flow through the solenoid creates a magnetic field that engages a plunger. The plunger closes the main contacts that provide high current power to the motor directly from the battery and engages a small gear with the engine flywheel, which allows the motor to turn the engine over. The diagram now shows the starter motor represented by the solenoid and the DC motor symbols. We will also add the battery cable running from the solenoid contact to the battery and the wire running from the solenoid to the ignition switch. We will now expand the ignition circuit and include a fuse box and additional components. First, we will add 4 fuses to the switched ignition line and move the ignition light to a fused position. Next, we will connect 2 switches to the ignition fuses that switch ignition to light bulbs. These switches resemble a brake light switch and reverse light switch. Measuring tools. A multimeter is used to measure voltage, ampere, and resistance. Set the multimeter to DC voltage when testing voltages to determine constant power and switched ignition circuits. Voltage is potential difference and therefore you need to measure across the load of the circuit. Ground the black lead on the body or chassis and use the red probe to check the voltages on the circuits. We will now use the circuit built earlier to indicate voltage readings at specific points. Connect the black lead from the multimeter to ground. Connect the red probe to the wire that will provide ignition power to the ignition light. With the switch off, the voltage reading is 0 volts as no current can flow. Turn the switch on. The voltage reading is 12 volts as current can now flow through the multimeter. Now connect the red probe to the wire between the door switch and the light with the switch off. The voltage reading shows 12 volts, although the switch is off. This is because the multimeter probes can measure the potential difference as the multimeter completes the circuit. Thank you for watching our Introduction to Automotive Electrical Systems course. We trust that you have gained an understanding of a basic automotive power circuit, the various symbols, and how to use a multimeter to measure voltage. Please visit our website and subscribe to our YouTube channel to access other courses we offer.